In this video, we're going to look at some properties of matrix operations. So I've listed out 5 key properties of matrix operations, and most of these I think are pretty much what we'd expect to happen. Like for example, property 2 says, if you multiply a matrix A, times B plus C, multiplying by A sort of distributes, and I get A times B plus A times C. Okay, so most of these I think are kind of what we'd expect to happen. So now I want to talk about something more interesting. There are some properties that we might expect to happen, but they are not true for matrices. Like things that happen in just like regular arithmetic, but just are not true for matrices. And those are these 3. Okay, so the first thing that's not true for matrices is when you switch the order in which you multiply matrices, you're not necessarily going to get the same thing. One sort of conceptual reason why is, remember that multiplying by matrices sort of corresponds to composing 2 functions. So on the left-hand side, let's just imagine we have something like f of g of x, composing 2 functions. On the right-hand side, we're switching the order to g of f of x. But we know from our knowledge of algebra, hopefully, that these 2 things are not always the same. These are not always the same in general. So the first time we see something like this, it's weird because it operates in a way that's different from what we're used to seeing with numbers. One other way to sort of convince ourselves why these may not always be the same is, let's just imagine that A was something like a 2 by 3 matrix, and B was a 3 by 2. Well, when I multiply them together, I would get a 2 by 2. But if I did it in the opposite order, if I did B times A, well, B is a 3 by 2 matrix. A is a 2 by 3 matrix. So when I multiply these, I would get a 3 by 3 matrix. So it's not even the case that when I switch the order that I multiply my matrices in, that I'll always end up with something of the same size. And if that's the case, the products definitely wouldn't be the same. Okay, so why is 2 not necessarily true? So if I multiply 2 matrices and it equals 0, so when I say 0 here, I mean the 0 matrix. So that's a matrix that just has zeros everywhere. It doesn't necessarily have to be 2 by 3 like the one I just drew, but I just meant to say that there's zeros everywhere. It's not necessarily the case that A is the 0 matrix or B is the 0 matrix. As an example, so this time I'll give you guys a concrete example. If we take the matrix 0, 1, 0, 0, so this is not the 0 matrix because it doesn't have zeros everywhere. It has at least one thing that's not a 0. And I multiply it by itself. So both of these are not the 0 matrix. If you multiply these, and I'd encourage you guys to do this on your own, it'll just take a few seconds, it ends up being a matrix of all zeros. And that's pretty interesting. I can multiply 2 matrices that are not just the 0 matrix, such that their product is the 0 matrix. Okay. The third property says if I have A times C being equal to B times C, it's not necessarily true that A equals B. In other words, I can't just sort of cancel the C away. So one way to see why, in terms of translating it back to functions, so the left-hand side would be something like f of g of x. So that's sort of like the A times C. The right-hand side would be like saying that this is equal to like h of g of x. So I have the same function on the inside because both of these matrices are multiplied by the C on the right. So if that was the case in terms of functions, it does not necessarily follow that f of x equals h of x. That's not a property of functions. So I think that sort of translates to seeing why this is not necessarily the case for matrices. There is a scenario which we'll learn about once we talk about invertible matrices, where we can cancel the C out, but we can't do it in general. Okay, so next let's define a new matrix operation, which is called the transpose. Okay, so the transpose of a matrix A is denoted by a t. So the t is written in the exponent, although it doesn't mean it's an exponent. It's just, we just notate it that way and we say a t, or a transpose. The way this is defined is using this So this formula, what this is saying is the transpose switches the roles of the rows and the columns of the matrix. So it's easiest to explain what I mean by that by doing an example. So let's find the transpose if my matrix is 1, 2, 3 in the first row, and then 4, 5, 6 in the second row. Okay, so let's write out what the transpose is. Okay. So what's going to happen is the first row of A becomes the first column of the transpose. So this first entry is in row 1, column 1. So I switch the roles of the rows and the columns. So that just stays where it is. Still row 1, column 1. The next entry, the 2, right now, this is in row 1, column 2. So in the transpose, it would be switched. It would be row 2, column 1. And that's where the 2 gets placed. The 3 would get placed underneath that. Basically what's happened is, I've taken the first row of A, and I've made it the first column of the transpose. Let's do the same thing with the second row now. The second row of A becomes the second column of the transpose. So just 4, 5, 6. If we just remember that the transpose switches the roles of the rows and the columns, that's the quickest way to remember what it does. Okay, so now I want to state the theorem about the transpose. Okay, so there are a few properties that the transpose has that I want to state for us. Okay, so the first one is if you take the transpose, and then you transpose that again, you'll get the original matrix. Basically, that's saying if you switch the rows and the columns, and then you do it again, you just get the same thing that you started with. Okay, and then we have these other properties of the transpose, so property 2, 3, and 4. The one that I want to point out that may be a little bit, non-intuitive is property 4 right here. Because in property 4, notice that if you multiply two matrices, you take the transpose, then their order switches, so you'd have the B first and the A second, and you put transposes on both of those. So I'm not going to give you guys a proof of this theorem, because I think our time is more worthwhile being spent doing examples rather than proving this theorem. Okay, so let's end with another example. Okay, so let's say that A is the matrix here, and I want to find a non-zero matrix B with different columns such that A times B equals 0. And when we're at 0 here, we're talking about the 0 matrix. And that should be clear from the context because A and B are matrices, so when I multiply them, I should get a matrix. So how do we solve this? Well, so I have the matrix A, 1, 2, 3, 6, and I need to multiply that by a matrix B. And actually, I forgot to mention one thing about B. I forgot to say that B is 2 by 2. So I want B to be a 2 by 2 matrix. Okay, so I don't know what the entries of B are, so let me just call them A, B, C, and D. And I want this to be equal to the 0 matrix. So this is 2 by 2, and this is 2 by 2, so the product is defined, and it's going to be 2 by 2. And I want this to just be all zeros. Okay, so this is true if and only if. Let's multiply out the left-hand side. So the left-hand side, if I multiply these matrices, I'll get 1 times A plus 3 times C for the first spot. So A plus 3C. Then I'll do the second row of A times the first column of B. So I'll get 2 times A plus 6 times C. Okay, now I do the first row. So I've multiplied all the rows of A times the first column of B. So let's multiply the rows of A times the second column of B. So first row of A times the second column of B gives me 1 times B plus 3 times D. And then I do the second row of A times the first column of B. So I'll get 2 times B plus 6 times D. So that's supposed to equal the matrix of all zeros. So for these to be the same, each of the corresponding entries has to be the same. So for example, this entry has to match up with the 0. So I need A plus 3C to be equal to 0. If I look at the second entries here, So what I mean by that is, the ones that I've just circled in red, I would get the 2a plus 6c has to be equal to 0. And then the same's got to be true for the b plus 3d and 2d. Sorry, I think I miswrote this. I shouldn't have said 2d. Maybe you guys actually caught that and already wrote it correctly. This should have been 2b when I multiply the 2 times that b. Okay, so writing those, I get that b plus 3d needs to equal 0, and 2b plus 6d needs to equal 0. Okay, so I need to figure out what a, b, c, and d could be in these equations to make them all true. Okay, so one thing to notice is that these two blue equations, they're actually equivalent. If I multiply b plus 3d equals 0 by 2, I get this bottommost equation. So these are equivalent, because I can get the one from the other by multiplying by a constant. The same thing is true about these green ones. They are also equivalent. I can get the second green equation by multiplying the top one by 2. The other thing that I want you guys to notice is that in the green equations, my only variables are a and c. In the blue equations, the only variables are b and d. So when I solve for a and c, I only need to work with the first two equations, because the second two equations don't tell me anything about a and c. Okay, so let's work with these two equations to figure out what a and c are. But because these two equations are equivalent, I only need to work with one of them. And if I only work with one of them, I'm actually going to get an infinite number of, let me say, values for a and c. Because the second equation is sort of equivalent to the first. And if I just work with the first, I could pick whatever I want for c, like maybe I'll pick c equals 1. And if I did that, I would get that a has to be -3. So I could do the same thing for the blue equations. Just to show you guys I can pick something different, maybe I'll pick d equal to 2. And if I did that, I would get that b has to be equal to -6. And now I have the values for my second matrix. A is -3, b is -6, c is 1. And just as a check, I've written over here on the side that if I were to multiply the matrix A times this matrix B that I've just found, if you were to check it and multiply everything out, it does give us the 0 matrix.